GenAI and MLOps Part 2. This episode has 12 questions. For each question, take a moment to think through your own answer before I share a strong approach. Question 1. LLM Ops or GenAI production. A GenAI feature's inference cost grew 5 times in a month. How would you investigate token usage, caching opportunities, model selection, and prompt length before cutting features? Here's a strong way to approach it. Break down cost by feature, model, and request type using logged token usage to find exactly what grew and why. A common cause is a prompt template that grew, more context, more few-shot examples, or a shift to a more expensive model without a corresponding quality justification. Look for caching opportunities on repeated or templated queries before considering feature cuts, and evaluate whether a smaller or cheaper model would meet quality requirements for a meaningful portion of traffic, since model selection is often the single biggest cost lever. Nice. Let's continue. Question 2. LLM Ops or GenAI production. How would you defend an LLM application against prompt injection and data exfiltration from untrusted user input or retrieved documents? Here's a strong way to approach it. Treat any retrieved or user-supplied content as untrusted data, not instructions. Use clear structural separation, delimiters, system versus user role boundaries so the model is less likely to treat embedded text as a command, and validate or filter outputs for signs of instruction following from injected content. Limit what the model can actually do with a successful injection by keeping tool access scoped and requiring confirmation for sensitive actions, since defense in depth matters more than any single prompt level mitigation, which can't be made fully robust. Great. Moving on. Question 3. LLM Ops or GenAI production. An AI agent can call internal tools and APIs. How would you sandbox tool execution, enforce least privilege, and prevent unintended destructive actions? Here's a strong way to approach it. Scope each tool's credentials to the absolute minimum permissions needed for that specific action, never granting the agent broad standing access, and require explicit confirmation, human in the loop, for any destructive or hard-to-reverse action rather than allowing full autonomy on those. Run tool execution in an isolated environment separate from the agent's reasoning process. Log every tool call with its inputs and outcome for audit, and set hard limits, rate limits, scope restrictions, that can't be overridden by the agent's own reasoning, regardless of how it was prompted. Alright, next question. Question 4. LLM Ops or GenAI production. How would you build an automated evaluation and regression suite for LLM output quality before shipping a prompt or model change? Here's a strong way to approach it. Build a fixed set of representative test inputs with defined quality criteria, either exact match for deterministic cases or LLM as judge or rubric-based scoring for open-ended ones, and run every prompt or model change against this suite automatically in CI before it can be merged or deployed. Track scores over time to catch gradual regression, not just pass or fail on a single run, and require a human review of any significant score change before promoting the change to production, since automated evaluation can miss subtle quality issues a person would catch immediately. Let's keep going. Question 5. LLM Ops or GenAI production. What would you trace and log for an LLM request end-to-end, including prompts, retrieved context, token counts, latency, and model version, without leaking sensitive data? Here's a strong way to approach it. Log the prompt template used, not necessarily raw user input if it contains PI, retrieved context references, document IDs rather than full content where sensitive, token counts and latency broken down by stage, retrieval, inference, post-processing, and the exact model version or deployment that served the request. Redact or hash any detected PI before it reaches logs, and store full unredacted traces, if needed for debugging, in a separate, access-controlled system with a much shorter retention period than regular application logs. On to the next one. Question 6. Kubeflow. Kubeflow platform design. How would you design a production Kubeflow platform on GKE for notebooks, pipelines, training, serving, security, and observability? Here's a strong way to approach it. Run Kubeflow on a dedicated GKE platform with separate namespaces or profiles per team, GPU and CPU node pools, workload identity, artifact registry, cloud storage, and centralized logging or monitoring. Provide managed notebook access, Kubeflow pipelines for repeatable workflows, training operators for distributed jobs, K-serve for model serving, and platform guardrails such as RBAC, quotas, network policies, image scanning, backups, and clear ownership for each component. Good. Here's another one. Question 7. Kubeflow. Kubeflow pipelines. How would you design a reusable Kubeflow pipeline for data validation, training, evaluation, registration, and conditional deployment? Here's a strong way to approach it. Model the workflow as containerized components connected by typed inputs or outputs. Validate data, transform features, train, evaluate, and only register or deploy if metrics pass thresholds. Store artifacts in object storage. Record metadata for lineage. Parameterize environment-specific values. Enable caching only when cache keys include data or code or config versions. And keep deployment as a conditional step so bad models stop before production. Nice. Let's continue. Question 8. Kubeflow. Kubeflow multi-user isolation. How would you isolate teams in Kubeflow using namespaces, profiles, RBAC, service accounts, quotas, and network policies? Here's a strong way to approach it. Give each team a Kubeflow profile mapped to its own namespace, service accounts, resource quotas, and role bindings. Restrict cross-namespace access with RBAC and network policies. Use workload identity for least privilege GCP access. Apply separate CPU or GPU quotas to prevent noisy neighbors. And tag or label workload so usage, cost, and ownership are visible. Great. Moving on. Question 9. Kubeflow. Kubeflow troubleshooting. A Kubeflow pipeline step is stuck pending or failing. How would you debug pods, volumes, service accounts, images, logs, and events? Here's a strong way to approach it. Start with the pipeline UI to identify the failed component, then inspect the underlying pod with kubectl, events, scheduling reason, image pool errors, volume mounts, service account permissions, resource requests, node selectors, and logs. Pending often means quota, node capacity, taints or tolerations, PVC, or GPU availability. Runtime failure usually points to container command, dependency, data path, or permission issues. Alright, next question. Question 10. MLflow. MLflow tracking design. How would you structure MLflow experiments, runs, parameters, metrics, tags, artifacts, and naming conventions for a team? Here's a strong way to approach it. Create experiments around stable business problems or model families, not every individual run, and use consistent run names that include project, branch or pipeline run, and purpose. Log hyperparameters as params, evaluation results as metrics, model files and reports as artifacts, and use tags for owner, git commit, dataset version, environment, feature set, and candidate or prod status so runs are searchable and comparable across the team. Let's keep going. Question 11. MLflow. MLflow model registry. How would you use MLflow model registry for versioning, approvals, stage transitions, aliases, rollback, and auditability? Here's a strong way to approach it. Register only evaluated candidate models. Attach metadata linking the model version to the MLflow run, git commit, dataset, metrics, and owner, and require an approval step before promotion. Use stages or aliases to identify candidate, staging, and production versions. Keep older production versions available for rollback, and record comments or approvals in the registry so model promotion is auditable rather than a silent artifact overwrite. On to the next one. Question 12. MLflow. MLflow on Kubernetes. How would you deploy and operate an MLflow tracking server on GKE, including database, object storage, ingress, auth, and monitoring? Here's a strong way to approach it. Deploy MLflow as a stateless Kubernetes deployment. Use Cloud SQL or Postgres for the backend store, GCS for artifacts, workload identity for bucket or database access where possible, and an ingress or internal load balancer protected by SSO or IAP or an auth proxy. Add resource requests or limits, health checks, TLS, backups, audit logging, dashboards for request errors and latency, and alerts for database or artifact store failures. Good, here's another one. That wraps up this episode. Nice work practicing, and see you in the next one.